Hi there. Thanks for coming. So, um, so I'm going to tell you about how to synthesize attacks on protocols. So I'm going to start by saying what the problem is that I care about, and then I'm going to uh, tell you what I'm assuming about protocols, and then the third part of this talk is going to be uh, showing how to synthesize an attack on a protocol. So the setup is we have a protocol and we want an attack on it. So normally we think about this as a design problem, and to design an attack, you need to um, understand the weaknesses of the protocol and then figure out how to exploit it. And okay, so what does design mean? For us, it means that um, we want to learn what attack is going to work. And so the way that we do that is by guessing and then testing our guess and then updating our guess based on how it's doing on the test. And then repeating this process until the test passes or we see evidence that this iteration is not helping. Um, so that's the setup. Okay, so what are we working with? When I say a protocol, I mean there's a set of roles and channels for communicating from one role to another, whose implementations are given by programs. And the protocol specifies requirements that it wants to hold on the channels and the outputs of the channels. And again, the protocol depends on programs, and in particular, you're feeding in inputs. The inputs come from somewhere, and sometimes you explicitly model them as coming from other protocols. So sometimes the inputs are so constrained that sort of the protocol specifies everything there is to know about them, but sometimes there is flexibility. So maybe the protocol says, um, I want the user to send a random number to this other user. If the protocol doesn't explicitly specify what what random number generator one of the users should be using, um, then that input comes from somewhere. So it's either specified by the protocol or specified by something external to the protocol. Um, and when you leave things not explicitly specified, when you leave things um, so that they are not explicitly specified by the protocol, then this is an attack surface that opens up opportunities for other protocols to design inputs adversarially. And so that's sort of the setup in this legendary paper by Kelsey, Schneier, and Wagner on protocol interactions and the chosen protocol attack. So the idea in their paper is you want to attack one target protocol T, and so you're going to design a different chosen protocol C and induce the user to interact with this protocol with the same, um, basically with the same program that he's using in the other one. So if in the target protocol he is encrypting messages with some key, then you want to induce them into using the same key signing mechanism in this other protocol. And then so that's the way that they're interacting, that the victim is sharing this program in the two protocols. So you need to design a protocol that is good enough and sort of on the surface secure enough for the victim to want to use it. You need to induce them to use it, um, and um, and the idea is you want both of these protocols to look secure, um, sort of in their own right, but that when you are using them together, that there is some problem um, that you want to exploit. And so I think there were three big ideas in their paper, and the two big ones are in the title. One is protocol interactions. So one of the big ideas is that protocols can interact with each other in ways that that maybe neither of them have had explicitly considered. So that's one. The other one um, is the idea that that uh, that there is a specific thing you can do to break um, some of the requirements that were held implicitly by the target protocol, and um, and so one of the big ideas there is that the an attack on a protocol T isn't just a program; it's a whole protocol that you can design. So an attack on a protocol is a whole protocol. And so the idea for us is to sort of figure out how your attack is going to slot into the target, and then, but like without worrying about what exactly you want it to do, just recognize what attack surfaces are open. Maybe if it's like a client-server protocol, and somebody else is running the server, you get to design the client program and sort of choose what you want for what messages the client is sending to the server. And so in the first step, don't worry about it, just worry that it's going to slot in correctly, you know what needs to talk to what. In the second step, you're going to actually learn sort of the optimal strategy for attacking the target protocol. Okay, so this talk is going to sort of happen on two levels. The first is the high level. We're going to talk about what exactly we mean by protocols. And there's a bunch of different meanings. Like at a super high level, it's just a specification that you want some things to happen. These sort of message passing systems are implemented with computer programs. So at some levels, it makes sense to model that explicitly. At the end of the day, these things actually run. So there's executable software running on real hardware. So that's one level of analysis that you could think about. And for some parts of the protocol, you could say you're not even really implementing the program in C. You get to, like the protocol leaves it open, you get to choose. And so some of those things we're going to be able to implement with neural networks, for example. Okay, and so at a high level, there's different aspects of a protocol that are worth considering for different problems that you want to solve. And so there's sort of two things at a low level that we care about. One is sort of thinking about how to formalize what it even means for two protocols to interact. That's sort of what I mean by models. And then to give this model some teeth, we want to actually consider an example where there is a secure target protocol T in isolation, where the requirement sort of breaks down specifically because of this interaction with another protocol. And so sort of on the left, models, we're going to formalize definitions, and on the right, I'm going to show outputs of some code that I've been writing this week. Okay, so one of the things that's in a protocol is there is a role. So some actor has some behavior that is specified by the protocol. So one of these I'm going to call Alice. I'm going to denote it with A. But there's more than one role. There's a bunch of roles. For now, I'm going to restrict attention to a protocol with two roles, Alice and Bob. And each of them have their own data type, called A and B. And you can consider sort of the joint data type, A times B, as sort of consisting of these two pieces. Okay, so what I mean by message passing is that Alice can send a message to Bob. And the way that she does that is by doing some computation. So Alice passes an input into the channel, which computes some message in the language that Bob is prepared to read it. Okay, and then there's another channel H from Bob to Alice. And you can think about composing these things. So like a prompt response pattern would be Alice sends a message to Bob, who then responds to Alice. So that's this diagram on the left, G and then H. And then on the right, you could do H and then G, which is Bob prepares a message, uses H to transmit it to Alice, who then uses G to transmit a response back to Bob. Okay, and then you can compose these channels when the endpoints sort of match up in the way that you would want. Okay, and then there's this other, so A is a data type. There's this other data type called I, which is the unit, which just does nothing. So a state of Alice and a state of the unit is no different from just a state of Alice. And there's a special transformation, the special channel, that transforms a state of Alice into a state of I, which we think of basically as deletion. And one of the like data type products that we care about the most is just two states of Alice. And the reason why, so this is this equation on the top, the reason why we care about this is because we are going to think of one of these states of Alice as persisting and this other one as changing. And so we're thinking of encoding Alice states, but one of them is persisting and one of them is sort of changing dynamically because of this communication with Bob. And so one of the things that we're going to use is this channel on the bottom that takes a state of Alice and copies it into two identical copies. And so you can think of it as emitting one pair of states or two states. Okay, and so whenever you have two states, you can pick out the one on the left or you can pick out the one on the right. Okay, so one of the things that you need to model stateful computation is that whenever Alice sends a message to Bob, that doesn't just become the state, that doesn't like totally determine the state of Bob. Bob accepts this message and then uses his current state to update. So that's this rectangle on the top, UB. And so update takes in an incoming message and a state, and then spits out two things: the new state that he's going to keep internally, and possibly an outgoing message that he's going to send to somebody. Okay, so so what I mean by a stateful protocol is that channels from one role to another one are followed by an update. And so I'm denoting this with this new rectangle on the left called TAB, because it's like Alice sending to Bob. Okay, and then we can have the other way around. Whenever Bob sends a message to Alice with H, Alice is then going to accept the incoming message, but then update the state and message. Okay, and so on the left, I'm denoting this with TBA. Okay, so when we have a protocol with two channels from one role to the other, and each of them has their own updates, then we get this way of transforming A's into B's. And so you start off initially with two states of the sender, the actual state that they have, and the message that they're going to transform. And then you end up with the flip, that in the end, their state persists, but now the recipient has two states. The one that is the updated persistent state, and then the one that could possibly be used to send outgoing messages. And so we have one of these for each channel. And so if you look at sort of what the data types are for the outgoing and incoming wires, we can stack these. So one of the things that we could do is we can run first Bob sends a message to Alice with H, which is followed by an update, which then which then we separate the pieces, and then Alice uses G to send the message to Bob, which then updates. Okay, so this is basically just saying, using updates the way that we want, basically Bob sends a message to Alice, who then sends a message to Bob. So this is one pattern that we can have. And the protocol specifies which channels are there, and then that they're followed by update mechanisms, and then sort of which orders of things are allowable. Okay, so to give you a specific example of a two-step protocol, I'm going to say I'm going to give you an example. So Alice has some bit that's either 0 or 1. She chooses at random before the beginning of the protocol. And then the protocol begins when Bob sends a message to Alice. His message is either a 0 or a 1, and it's a guess about which bit Alice has in secret. And Alice responds with a simple yes or no. Yes if the guess is correct, no if it's not. Okay, so you can think maybe as like you would use it as a mechanism to prevent, for example, serving bots. You just want to make it harder to serve clients. Okay, so you can ask, well, what is the probability that Bob is going to guess correctly? He probably cannot guess correctly every time, because this is essentially like a one-time pass sort of thing. So he probably cannot guess correctly 100% of the time, but he can guess correctly sometimes. And your intuition is that if Alice is picking uniformly at random, that he should be guessing correctly 50% of the time. And then we're going to think about running this protocol a bunch of times. So maybe Alice chooses a new bit at random every hour, but Bob is only allowed to interact once an hour or something like that. Okay, so what's the probability that Bob is going to guess correctly on any one of these runs? 50%. So I am simulating that exactly. I'm showing, if you just look at the blue curve for a second, Bob is guessing Alice's hidden bit. I'm doing this for 100 trials, and the blue curve is showing Bob is correct 63% of the time. Okay, that's pretty rare, but that I think within that's within 3 standard deviations. And then I'm just going to do it again, do a second run just because to low sample I want to get a better sense. And this time Bob guessed correctly 44% of the time. So if we had done a single run of 200 trials, he would have been right about 54% of the time, something like that. So that's within reason. Okay, so now suppose Bob knows that he has. Okay, so suppose we run 2 protocols, 2 instances of the same protocol at the same time, because we're picturing Alice is a server, B is the client, and we're running 2 instances of this protocol because the server could be running this protocol with a bunch of different clients at the same time. And so Alice is playing the same role of A in many instances of T, unboundedly many, with different actors playing the role of B because they're different clients. And any one of them sort of operating by themselves would have about a 50% chance at being right, and they each get 1 guess an hour. But suppose Malcolm really wants access to this, so he decides to interact with Alice twice. So Malcolm is running 2 instances of the protocol. So in both, Alice is playing the role of A, and now Malcolm is playing the role of B in these 2 different instances at the same time, asynchronously. So he gets to choose sort of to step in each protocol as he wishes. Okay, one of the reasons why this is not a crazy setup is that that if you think about the role of B as being played by a user in some web service, then maybe it's locked into their maybe Alice is identifying Bob via an email address, and has reason to think that she is fairly successful at limiting users to one interaction per hour because she's keeping track of email address. Well, Bob can just use two different email addresses and sort of covertly interact with Alice in these two different sessions. Or if it's tied to something else, maybe Alice has some reason to think that she is really, truly, uniquely identifying B, but Malcolm finds some way to subvert that. So then Alice's picture is that all she needs to do is worry about making the protocol secure in one interaction with one person. But really, Malcolm is not denying that. He's exploiting a different problem that only arises when this protocol interacts with a different run of a protocol, in this case the same one. So we're not breaking the requirements of T, we're finding something that goes wrong because of a requirement that was left implicit for T in isolation. Okay, then Bob needs this extra thing because he's actually playing two roles. Instead of just having a persistent state and like another entry for sending and receiving messages, because he's playing both, Bob really has two persistent states, one for each protocol, and two slots for messages. There's other setups where you could picture Bob's state as something else, but this is just a simple example. Bob has sort of one state for each protocol, and what he really has hidden is this joint state. And so when he's interacting with one, he can use the joint state to and project out of that whatever he needs in this one interaction. But behind the scenes, he really has this joint state like over all of his interactions with the protocols. So that's one thing. So Bob has this update, or Malcolm was playing these roles, has this update mechanism. And then the other thing is that the way that each of these protocols starts is by we're saying, well, we're going to start by initializing the role of Bob and initialize the guess. So that's two things, but then we're doing that for each protocol. So Malcolm needs to start by initializing these four values, these four terms in B. Okay, so what do we have? We have this target protocol, this guess the hidden bit protocol, and then the other thing that we have is this update of sort of the joint state in these two instances of the protocol, and this term that initializes the values of everything. And for now, I'm thinking of these interfaces as I'm just saying I'm looking for a function that does this, and I'm looking for an initial term with these four entries that does this. But for now, I'm not specifying what they are, just sort of the signatures. These are the kinds of things that I want. And then other things I might throw into this interface are the things that the target protocol needs but does not explicitly specify, because it leaves up to the individual actors. Okay, so these are the ingredients, and I need to basically fill in the values for each of these interfaces. And so I'm going to stitch together, so Malcolm is playing in these two instantiations of the protocol, and I'm going to stitch them together in this way. I'm going to say, first Malcolm starts by playing the role of Bob and doing a guess response thing with Alice, and then using Alice's response to Bob and Bob's updated state, updating that. So now I have two new persistent states and two new outgoing messages. In this case, I'm only going to use one of them, and I'm going to use that new one as the guess to play this whole two-step protocol again. So that's the sort of the workflow of what Bob is going to be doing. And I'm going to summarize this with this um, schema on the left, that it's this map that takes in uh, the persistent state of A, and then these 4 states of B, and then also this other map B that picks out the specific initialization that I'm using. And so what I need to do, so that's what I need to do. So I need to fill in the entries for these 2 things. For the initial term that specifies my initial guess. In this case, I only need some of them. And then I have this update map, but I don't know what it is. I just hypothesize that one of them is going to help me attack this protocol. Okay, so then what I need to do as a programmer is I need to instantiate the schema in some way, define what the test is and what it means to be successful, guess some initial term and initial function, and then if the test is good, then I'm done. Otherwise, I'm gonna update in some specified way. I'm gonna update either the initial guess or the function that I want to learn, and then I'm going to test it, and then I'm going to repeat this loop of updating mechanically until something happens in the test, until I succeed, or until I stop making measurable progress. And so I have a demo of running this experiment with this guess the bit protocol, and so I'll walk you through what this slide is. So I'm doing that exactly, and then in the end, well, even before I train it, I'm just asking if I actually do this setup in this way that I've described, with some guess that I have for how good is it? Right? If I'm actually playing these 2-step protocol, how good am I at guessing? And the answer is, well, before I've done any training, just my guess was I guessed right 63% of the time on one instance, and on the other instance I guessed right 44% of the time. So my random guess basically really is random. So I have figured out some way to represent this, but then my initial guess, it didn't take any hard work, and that's reflected by the fact that it basically reflects random behavior. But then what I want is for my mechanical update to work, and so I'm going to show you the progress of this update over time. Okay, so there's 2 things to note. The first one is for the first 200 episodes, so for the first 200 trials that I'm learning from, the reward, I won't get into what exactly this is quantifying, but the reward oscillated basically between 0 and 0.5 and 1, right, in this range, for about 200 episodes. And then for the next 200 episodes, it oscillated between mostly between 0.5 and 1.5, with some stragglers of zeros. So there, even in the blue, there's this definitive upward shift. And then if I smooth it out, this orange curve is showing that the cumulative average reward really is going up over these 400 trials. So basically what I'm doing is I'm running the protocol. I have an initial guess. I run the protocol. I see how good it is, and then I update. And I do this test update 400 times. And it gets better. I mean, the blue is showing, it gets better sometimes, but it's pretty random. But over the long term, the orange is showing that it basically is consistently getting better. Okay, so now I'm going to compare this to the original. So now I'm going to show you what reward I actually care about. So this is the way that it works. I'm guessing twice, right? Once on this instance of the protocol, once on this instance. And for each one, I'm assigning 1 point if I guessed correctly, 0 points if I guessed incorrectly. And before training, on the left, you can see that both of my instances, blue and orange, added up to, were about 0.5, and their sum was about, and their average was about 0.54. Was also basically just random. And so their sum was about 1. And then after training, I have this interesting phenomenon that one of the instances is seeing, this orange one is seeing that it guessed correctly around 50% of the time. And this other one, the other instance, is showing that it got a reward of the blue one is showing that it got a reward of 1 pretty consistently. And so their sum added up to around 1.5. It was really close. It was 1.49. And so what this is showing is if it had genuinely guessed correctly on both instances of the protocol, then the reward should be 2. If it was 50-50, then the sum of the rewards would be 1. And what we're showing is exactly, it's splitting the difference at 1.5, which basically means that it's like one of them is getting it right 50% of the time, but then the other one is getting it right 100% of the time. So 0.5 plus 1 really is adding up to 1.5, 1.49. And so this is showing that that Malcolm is unable to learn how to crack the protocol, how to crack one instance of the protocol. That's why the graph on the left looks random. But Malcolm did learn how to play this coupled interaction of the protocol with itself. And so how could this have possibly gone unnoticed by Alice? This makes sense if Alice, who has this hidden bit, specified that she wants Bob to be unable to guess her hidden bit by some like cryptographic means. Like there's no probability distribution that Bob could sample from to do any better than 50% over the long term. So that requirement is sound. But this other requirement of, am I actually, this other requirement that Alice might want of limiting the amount that she has to pay out of correct marks is actually violated. And we did not specify the like strategy to Malcolm at all. We just specified basically this interaction diagram without UM or B. And in fact, we are always running it with B equals 0. But we're letting it learn UM. And so we did not dictate a strategy to Malcolm, and yet he learned this protocol of guess on one and then use Alice's marks to inform his guess on the other instance of the protocol. And so this is a very realistic way to cheat. This is literally how students cheat if you give them a quiz with unlimited attempts. And Malcolm was able to learn it just with this method of guess and update. Okay, so what is this method? Just to start wrapping things up again. We assume Bob knows this protocol. So he knows sort of what he is supposed to tell Alice and what Alice's responses would mean. And maybe he doesn't have a complete picture, but he wants to fill it in sort of as honestly as possible. So maybe he doesn't know that Alice is using a biased coin, but if he suspects Alice's coin is biased 0.5, he wants his system, his simulation of that to reflect like the real environment as much as possible. And then step 2 is draw this diagram. Basically, every channel that was left unspecified in the actual target protocol, because the actors were supposed to provide those programs, are unspecified, and so that's a thing that that can be adversarially designed. And so identify what is missing from the protocol. And there's sort of two things that are always missing. If the protocol has an output, it might, like you might get an error code or some other sort of output, even though they don't expect anything else to happen next in the protocol, you still get an output. And that is still possibly something you could learn from, even if that user is allegedly like burned from ever interacting again. Usually the output provides some sort of information about that you care about. Like maybe it says, sorry, this password doesn't work, it's too short. Or maybe it gives you a specific error code. And these are the things that you are using as learning signal. The other thing that is usually left unspecified is the beginning of the protocol. You normally start with some input. So in cryptographic protocols, you might start with a random number. There are some protocol attacks, like the ones in the paper by Schneier, that work precisely on because the protocol was expecting a random number, but what was provided was actually not random at all. It was like a user ID. So oftentimes the input, like the thing that is starting off the protocol, is the protocol designer assumes something without actually requiring it. And so that's another unspecified channel, is the input to the protocol. So so you just need to understand about the protocol what is not explicitly specified. And then think about all ways of feeding in information to the things that expect information, and everything that the protocol is leaking as output, absorb it, and then just think about naively all of the ways of completing the diagram by feeding in inputs, taking in outputs, and then closing the loop. So just close the shape that amounts to just drawing a diagram, right? And then fill in the diagram by saying, well, I needed actual channels here. Just guess what they are. You can just have a neural network just guess. And then if you have a neural network, for example, that is guessing, you can update the weights that determine the guesses. And so that means learning the neural network for each channel. And if you have a bunch of channels, learning the set of neural networks, which means learning the protocol that maximizes this reward of the attacker. So that's the method. Figure out what is missing, fill it in by guessing, and then update your guesses. Okay, so what have we done? So we've shown that to attack a protocol, that attack is a protocol, and you can discover the strategically optimal attack with protocol learning. And there's a method to do this. And basically protocol learning is picking one at random and then optimizing it. Okay, so then it's basically an optimization problem that we solve with computers. And so whether it's solvable or not is a matter of geometry and computability, but your intuition from training models is that basically, yeah, that this problem is generally solvable, but you formalize that with theorems from geometry and optimization and computability, and machine learning theory, but these problems tend to have solutions or approximate solutions or candidate solutions that are better than other solutions, basically because gradient-based optimization on differentiable structures actually converges to local extrema. And so there is sort of an existing theory of that lends credence to the idea that solutions exist. And then to actually find the solutions, you use machine learning. You actually do, for example, gradient descent or some other gradient-based optimization on neural networks. So you use neural networks to encode basically the transition function for each channel. You can do that with a neural network or with a transformer. And one of the reasons why you want to use a transformer is because transformers are, in a sense, literally Turing complete. If you think about them as maps from sequences to yes/no, for example, then transformers with self-attention and positional encodings fed on sequences really can be Turing complete and in fact simulate Turing machines. And then for all sorts of reasons, these things are universal approximators and they're Turing complete. So if there is a computational problem here to be solved, they're good candidates for them. Moreover, because they're like differentiable programs, they can actually iterate their guesses. Okay, and then in the previous slide, I said, well, there's a bunch of channels, and you have to figure out basically how to fill in all the ones that are left open, including these ones that were left open implicitly. But oftentimes you know sort of what shape your attack should have. And when you do, that often tells you, like, oh, there's this other part of the neural network that I am learning, but I'm actually could probably have an attack that doesn't even use it. Then you could cut your network in half or something like that. And so when you have an insight about what kinds of attacks can work, then you let yourself search basically a smaller space because you need to learn less function, basically, like less outputs or less inputs are relevant. And so this lets you refine the model architecture from the most naive one to the tightest one that you think is actually going to work. And this makes the task of learning easier, and it makes this problem easier to solve. And so there's a lot that you can do when you're totally ignorant of the attack, and that is, I think, going to turn out to be a well-posed problem, I think. But you can also cut the solution space if you do have some sort of intuition. And if the model just doesn't learn as well as you want it to, maybe your intuition was wrong, and then you can expand the search space. But oftentimes, you do have intuition, and there is a way to account for that. Okay, so the big picture is to synthesize an attack on a protocol. That is the problem of protocol learning, and there are methods for it. This is an emerging area with a bunch of new problems and new dimensions of other things, of other problems of interest. There's a lot of sort of intuition that we already have that comes from existing literature about why we think solutions exist, what shape these things would have, what kinds of methods we want to design. There's a lot to pull from in existing literature, but a lot of this is emerging research, right? Like if we're talking about learning a set of protocols, which is like a set of channels, which is what protocol learning is, then you are solving this then you want to solve for sets of conditional distributions, and that sort of thing is an area of interest that is gaining an area of research that's gaining interest. One other reason you would want to do this thing is you have a fleet of robots that have their own tasks, but they also need to solve some cooperative task. So this is protocol learning is the kind of thing that other people care about, but the theory isn't sort of fully fleshed out yet, and there's a lot to do here that is wide open. And in particular, empirical research is very lacking here. So there's adjacent case studies for, say, protocol learning for security, like for I want to learn how to do some steganographic task or cryptographic task, but this idea that the attack itself is a protocol that can be learned, as far as I know, has not been explored empirically at all, and so there are no empirical benchmarks that I know of. So this is a wide open field. Yeah, and it'd be really interesting if I guess one other thing to note is, like, a lot of the sort of research effort around protocols and attacks for them is sort of logical in nature. You think of them as formal specifications, or as programs that you would want to learn with program synthesis. And program synthesis is a really hard thing to do. So it's interesting that our empirical way scales with AI at exactly the kind of thing that neural nets and transformers are good at. So it's like solving the same sort of problem as that program synthesis wants to solve, but it's a totally different task. And then there's this other sense in which it is like a level up version, because even if you could do program synthesis, you're not doing it for one program, you're doing it for collections of programs that compose with each other. And so there's a few different reasons why it's different than what is traditionally considered. So the idea of synthesizing attacks with protocol learning is maybe more tractable than we would have thought. Yeah. Okay, thank you.